nice and does stuff for us so we don't have to, right? So now you're entering a time machine and you're making the herbarium like you are, 40 years younger. And then we're gonna enter that same time machine and we're gonna come back to the current time. All right, so there are two kinds of inference rules. There are structural rules that are present in every type theory, and then there are specific rules, for example, for Martinov type theory that I will present. And you see, I'm already hinting towards some of them are present in every type theory, right? And we'll look at those first. So these are really inherent, you can't have a type theory without these rules. Well, you shouldn't call it type theory then, in my personal opinion. All right, so let's look at the structural rules. There are the following 5 categories. So the first one is that the judgmental equality is an equivalence relation. And then we'll have something called the variable conversion, substitution and weakening, you already know from Brigitte, but we will see it anyway again. And then the generic element or the variable rule. I don't remember if Brigitte did it, but it's for sure an important thing. All right. So first, judgmental equality is an equivalence relation. So how many mathematicians do we have? Who is a mathematician? Okay. Who knows what an equivalence relation is? Everybody, good. You don't have to be a mathematician to know this. Okay. So an equivalence relation means it's a reflexive, symmetric, and transitive. Okay. So let's see how this translates. So above you have the typing rules, right? And these are like, if A is a type, then A is judgmentally equal to A, so reflexivity. Here you have the symmetry. If A is judgmentally equal to B, then B is judgmentally equal to A, and the same for terms, right? So if I have little a, then it's judgmentally equal to itself, and if I have little a and little b, then I can swap their order. And then there's transitivity. If I have A equals B and B equals C, then A equals C, and I'll say judgmentally once, and for both types and terms, okay? This shouldn't be very surprising. It's an equality, so we want it to behave as an equality. Okay. The second one is variable conversion, okay? So what I mean by that is if I have two types that are equal, so A and A prime, and then I have in my context something of type A, I can just pretend that this X is of type A prime, and this judgment, whatever here will be, is the same, okay? So I can just basically, if you will, rewrite this A to this A prime, and just leave this B, and it will, this rule claims, still be well formed, okay? So it's still okay. So I have here B of X is a type, but I could have any judgment, okay? So we can swap it for any judgment thesis here that depends on X. It should be the same, okay? Now, this is a conversion in the variable, so in the context. What we can also do is have element conversion, okay? And what element conversion means is that if I have a judgment that little a is of type big A, and big A is judgmentally equal to the big A prime, then little a is of type big A prime here. So here we swapped, we rewrote in the context, here we rewrote the type of the judgment itself, okay? So judgmental equality in this way is kind of powerful, right? So because I can just swap the type and it's still okay, so that's powerful.
Question?
Yes.
When you say element conversion is derivable, are you saying that you can, like the second rule is a consequence of the first rule?
Right. That's the next thing I wanted to say. Very good question. So there's a comment saying element conversion is derivable. This is not a rule that is posed. This is a rule that we can derive from the other rules, some of which you have seen before, and some of which will come in the next slides. And bonus, I will derive it for you in, wait 7 slides-ish, and it will be there. And this is a very important thing. This is a derivable rule, and it's not an axiom, so to say, right? It's not an inference rule that you have to pose. It's something that is true anyway. Okay. And then the famous substitution. Okay? So luckily, Egbert, the author of the textbook, chose the same notation as Brigitte for substitution. So we don't have to have this dispute here of how we write substitutions. So this notation here means that we plug in A for wherever X appears, right? And similar to Brigitte, I don't want to go into what is bound and what is not at this stage. But morally, this is what it is. All three occurrences of X are replaced with the term A. Okay. Okay, maybe at this point is a good place to say something about these variables that are here. Right? So I'm giving you these inference rules, and then I'm giving you examples in this teal color, because I want to say that actually we use these rules when we instantiate these little a and big A with concrete stuff, right? So let's be very precise. This X here is a variable, and this is a context. So the notation is cheating a little bit. We have some stuff in the context, then we have X is in A, but then we have some stuff in the context afterwards. So this is this delta. And this X here really is a variable, okay? This X here stays. Like here I have N that is a variable, and this variable stays N. All of the rest of this stuff are meta variables, okay? Question?
The J judgment, like...
Yes, judgment thesis, whichever one of the four.
Sorry, the J is like another variable. Yeah, that one. Like, elsewhere in our, like, the other rules, the judgments are like a structural thing that have meta variables inside them, and now we're abstracting over the judgments. Is this really like, should this be thought of as like a family of rules for each type of judgment, or is it?
Very good question. Okay, so this is a family of rules, but is this, you can think of this as us on paper being very lazy and not implementing four different stuff, like not writing down four different stuff. So this curly J here stands for judgment thesis, and this is us being lazy because it's the same 4 times and we don't want to write it 4 times. In the proof assistant, in the kernel of a proof assistant, it will be written 4 times. Okay, so it's not really, so this J here is not a meta variable. This gamma, A, yeah, delta, these I call meta variables because I'm giving you sort of a family of rules. This is how they look like, right? But when you want to derive something, you're going to use these rules instantiated with stuff, right? So instantiated with stuff is this example, right? I can have little a be 0 of type natural numbers. Okay, little n is actually a variable, right? But it doesn't matter whether it's x or little n. The context will tell me what the name is and what the type is. And then this suc stands for the successor function, right? Is also a type constructor of the natural numbers. Okay, so this is not a meta variable, it's not a variable, it's an actual constructor of the type theory that will come back later. I just had to have something for you to see what this is about, right? So these meta variables, ideally you wouldn't see them, right? Ideally everything you want to derive will be instantiated. And ideally in the proof assistant you're not going to see them. But they are there because we want to write this schema of rules and you want to see if it's like an instance of something that exists in the type theory, okay? So we do not manipulate with meta variables within a proof assistant. Us, as a user, the system will, but we are manipulating with variables in the context. Okay. Okay, so the substitution, yes, plugging in stuff. And note that if I am substituting here something for x, I also have to substitute everything in delta because, remember, delta contains stuff that depends on x. Everything is dependent, so we have to substitute in the rest of the context for whatever we're substituting. And then, don't be scared. Scary to rules. The point of them is saying that if you're substituting judgmentally equal stuff, that results in judgmentally equal types of returns, right? So basically if I have here a type judgment or a term judgment, and so not for the equality judgment, okay? And if I substitute for something that is judgmentally equal, so little a is judgmentally equal to little a prime, then whatever I get, this b, with substitution will be judgmentally equal, and the little b will also be judgmentally equal, if I have it, okay? Yes, question?
Yes, so in many simpler, I guess, type theories, you can actually derive the substitution principle. But now it's by definition.
Yes. Okay. Here, for the purposes of this lecture, yes. When you ask me about meta-theory of type theories, I will say you really, really want substitution to be an admissible rule, or an admissible rule. Because if you want to prove any meta property at all, you're going to suffer in substitution lemmas if you make substitution as your rule. Okay? So you are right. We could pose rules of Martin-Love type theory in a way that doesn't require substitution to be a fundamental axiom, an inference rule that you have to pose. But for the purposes of today and for the purposes of using a proof assistant, it's okay. Right? It will explain some stuff, how the proof assistant works, and that's my ultimate goal for today. But an excellent question. Did I miss any more questions? Just shout. No? All right. Then we have weakening. Okay? Weakening means we can just add stuff to the context and nothing bad happens. Okay? Particularly, we can add stuff anywhere in the context, and even though this delta here theoretically could depend on x, it doesn't have to. Okay? Be careful when you do this, because to strengthen the context is not that easy, but weakening you can always do. So we have any judgment thesis, right? And we can just basically add stuff anywhere in the context, and it's still okay. It's just a weaker judgment. So an example, I could have something like this. I have, right, if we're weakening, the type of the variable has to be well-formed, right? According to the context that came before it. Okay? So you can do some sort of iterative weakening if you want, but yeah, it has to be well-formed. So for example, here, you see, and already my example is wrong. Perfect. What is wrong with this example? Who can see it? Yes?
Either you need to put x of type n in the natural number type judgment, or you need to put y before x.
Perfect. Very good. Gold star. Yes. Here, you see, I said that it has to be well-formed according to gamma, and I did some sort of iterative weakening here. But yes, technically, if this should be an example of this rule, x of type n should be here, right? Because it's here, it should be here because I'm weakening with y, and the context should be here the same, technically. Very well. And then, hopefully the last rule, I think, is the generic element or the variable rule, okay? So, the generic element or the variable rule says that if I have something in the context, it's also the judgment, right? So it says, if I have x of type A in the context, I can derive x is of type A as long as this is true, but if gamma is well formed, this should be true anyway. Sorry, if gamma comma x colon A is well formed, this should be true anyway. But the point is that, if I have something from the context, it's like proving by assumption, right? I'm just using the assumption. Okay. And hopefully these are all of our structural rules. Yay! More rules are coming out, so don't worry. Question?
Sorry. Was there a reason that in substitution we were able to substitute the context partially? I mean, is there any structural significance because I couldn't notice any?
I didn't quite catch that. We're substituting context partially.
Yeah, we could, like, the substitution rule, the context before the variable were untouched, or the context afterwards were substituted?
Yes, so the reason for that is, okay, let's go back. The reason for that is because the context is dependent, right? So if I'm substituting little a, for x here at this point in the context, right? Then all of these stuff in gamma could depend on x. So now I have to substitute. But, in delta. In gamma, it doesn't depend on x. So that's why gamma is left here alone. Okay.
Got a couple questions.
Perfect. Where can you, okay.
Could you go back to the slide that defines the context?
That's a long way back.
So, is it saying that in order to be a context, it has to be the case that all of these already are types?
Yes.
And then,
So you sort of inductively generate your context, right? You start with the empty context, that is always a context, and then if you want to form x1 is of type A1, A1 has to be well-formed type in the empty context. Yeah?
in the weakening rule, there's also, you have as a premise that A has to be a type.
Yes. It may be redundant. Let's see. Okay, now here is not redundant, right? Because if we're weakening with x, we need to say that in gamma, A is a well-formed type, so that we can plug it in here. It's kind of like building context. So this rule here, so A could be dependent on everything from gamma. I'm just not writing it. Does that confuse you? No, okay. A depends on everything in gamma. And A has to be a well-formed type for us to extend gamma with x, right? And then everything in delta is well-formed if we just take stuff from gamma anyway. So this together will be a well-formed context.
Okay. I think what was confused, I was reading it bottom up, but you're reading it sort of top down.
Yeah, well, the bottom thing is the conclusion, and the top are my premises, right? Are my hypotheses. So it's a hypothetical judgment, so to say, right? If I can derive that A is a well-formed type in gamma, and if I can derive this, then I can derive whatever is in the bottom of the tree. Okay. Question?
Why don't we have contraction?
So strengthening of the context, you mean?
Yeah.
Well, it's just not true in general, right? So you have to check that there are no dependencies, and that's not something you can just do syntactically, easily.
Can J contain X?
Yes. No. Sorry. I was just reading the bottom thing. Because of this, no, X should be a fresh variable that is not in gamma or delta.
So can one element be assigned multiple times?
I didn't hear that.
Can one variable or element be assigned more than one times in the context?
No. So these, good. The variables in the context have to have distinct names.
So you've been saying that the types in the context have to be well formed, but is that like an axiom, or is that a theorem that you can prove inductively based on like sort of a proof tree?
So if you want to have, so if I want to, I'm not quite sure what the question is. So if you want to operate with derivations, these derivations should have well-formed contexts for you to be safe, sort of to say. You can derive stuff with ill-formed context in principle, right? So going back to the meta-theoretic view, when I said, when we properly define what a type theory is, there is something, so there is a stage where you can say, okay, the context could be anything, it could be gibberish, and then you strengthen that assumption for the context to be well-formed in the end, right? So there, you could have an intermediate level of defining a type theory where the context could contain something that is ill-formed, but then, if you hypothesize something that is ill-formed, then, garbage in, garbage out.
I think the question was more like if we can prove definitely that A is a well-formed type, and if there's rules for when a type is well-formed. Is that correct?
I'm not sure.
Okay, yes, there are rules, so we will see that. So once we're done with the structural rules, we'll go to the specific rules, and you will see, like, if I want to have a function type, right, I can prove that the function type is well-formed if the domain and the condomain are well-formed, and then let them go on and on. Right, so...
Sorry, what was the question?
The question was the previous question related to what Martin Löf described as W types? So it is related to, it's not the same thing. So let's leave it at that, and we can talk on another occasion. More questions? Wow.
Yeah, sorry. I in the same vein, we haven't really said what a type is yet, right?
Yes.
Okay, so a type exists kind of outside of the context of this, and we're just able to, these rules are basically saying we can instantiate variables from the universe of types, whatever those are.
We can instantiate these meta variables. You mean like this big A here is a meta variable, right? And I'm instantiating here with the type of natural numbers, right? And we will introduce the type of natural numbers in a few slides.
Okay.
So yes, this is precisely what I'm doing. The structural rules are, present in every type theory, so to say. And in every type theory means that whatever type whatever types that type theory has, whatever specific, types they have, we can sort of instantiate this stuff with that. Okay. Am I through with the questions?
I have one quick question. With this specific example, nat is not representing type in any way, right? So
Yes, it's not.
technically x and y, you could put y in front of x in the bottom.
Yes,
And that's fine. Okay.
and that's fine, yes.
Okay.
So, like somebody said there are two ways to fix this mess. One is to put x here, the other one is to swap the place of x and y here, and both are correct, but not at the same time. Okay. So, more questions?
Can the context only contain simple variables or types, or also these judgmental qualities?
Context cannot have judgmental qualities.
Okay, so it's always variable type.
Yes, it's always variable colon the type. Yes, type, judgment, whatever. Okay, good, very well. Now we know about the structural rules. Now we can make some derivations, okay? So what are derivations? Derivations are finite trees where nodes are the inferences or inference rules, the root is the conclusion, and leaves are the hypotheses, okay? So let's try to make a derivation, okay? The one that I promised you, okay? I'm trying to derive here, with your help, that element conversion rule holds. Let me just grab it. I will press really hard. Okay. So how do we make make derivations, well, Brigitte just did it yesterday, right? She always started from the bottom, right? What are we trying to prove, right? This should be our conclusion. So my conclusion is in context gamma, I have type little a of type A prime. And now I am kind of telling you, lying a little bit, but kind of telling you that the structural rules that you saw so far should be enough to derive this judgment. So above here, I have my hypotheses. So we have a judgmental equality of types in this, and this is my conclusion. So my question is, which one of these rules should we apply in our last step to get that little a has type A prime? Why substitution? It's the correct answer, but I'm just...
Because it's the one that has, it's the one that has the equality with the judgment equality. No. Or, it's not because of the reason I thought.
Good. Yes?
Yes, because this is the only one where we can get a concrete element onto the right-hand side.
Yes. Because all of the others don't fit, yes. All of the other shoes are of the wrong size, in some sense, yes. So this is the only one that we can. So for example, we couldn't do we could do variable conversion, maybe, but we don't have any specific variables in gamma, so that shoe doesn't fit. We don't have judgmental equality in the conclusion, so all of these are gone. What else do we have? Weakening, again, we just have the gamma, so not going to work. Generic element, no, because the conclusion is not a variable, and then we're out. So it's going to be a substitution. Okay, good. What are we substituting with what? So, it's going to be substitution. No, we have to substitute a variable. So a term for a variable. Where is the variable? Little a is a term, yes. So we know that it's going to be substituting big A for some variable that I have to make up, right? So So let's look at the substitution rule again. Right? So here I am substituting what for what. So this big J now is my yeah, so this big J is my judgment thesis, and it's going to be a term judgment. Okay? So I'm substituting little a for x. That's okay. I have to extend my gamma with x of some type, and we have to know that little a has to be of the type that I will write here. So which type should I write here? Okay. I really love that you said A prime. Because now it looks like a cyclical thing. This and this is the same. Yeah, I love it. A prime was not the answer. Yes, the other obvious candidate. Good. So now we see that this one is already okay. This one is one of our hypotheses, so it's okay. The other one, we still have to derive. And how are we going to derive that one? Yes?
With the other substitution rule, not substitution, what's the name? The type changing type rewrite rule.
This one, variable conversion. Is that a question?
Sorry, I'm a bit confused right now. Why is the one on the left tougher but the one on the right?
Why is the one on the left? What?
You said the one on the left we already had.
Yes,
Right,
yes.
so on the left, like, why?
Because what I'm trying to prove is that if I have this guy and this guy, I can have this guy. And this guy is the same as this guy that I already have.
They're trying to prove the rule on the bottom.
What?
They're trying to prove the rule on the bottom.
I'm trying to prove, I'm really
Yes.
can't hear.
The rule on the bottom of the slide is what she's asking.
Yes, I'm trying to prove this, yes. That's the one that is derivable, and now I am deriving it for you. Right? And what does the derivable mean? Right? It means that I can make a derivation where the leaves are my hypothesis, and these are my hypothesis, and the conclusion is the same as here. Okay? So because this now can be a leaf, because this is my hypothesis that I am hypothesizing that is true. Hope this is a word. Okay, are we happy? We still have to derive this one. How do we derive this one? There was already variable conversion. Okay, we already have it on the slide. Okay, so how do I apply it?
Yeah, we rewrite the other way around, right? We rewrite A prime to A and have x of A prime, gamma x of
Yes.
A prime is derived
Yes.
as x of A prime.
Okay. So here, I told you that it could be any judgment thesis, right? So now I have a term judgment thesis, that's okay. So I want to rewrite to A prime, A prime to A, right?
So we have one judges A equals A prime judgment.
Right?
Yeah.
And then, what else do I need?
Judges that x is A prime and x is A prime.
It doesn't matter because it's multiple installations, but A and A prime should be swapped in the first one.
No.
No.
Because we're rewriting not from A to A prime this time, but from
Yes.
A prime to A.
Yes, because here in the conclusion is A and not A prime. So we're writing from A prime to A. And, yes, you're correct. Our hypothesis looks different, right? So we do have to use the symmetry relation. And this is our hypothesis. So Anja is happy, so you should also be happy. Yes?
The judgment thesis and the conclusion is type, not form. Does that matter?
Yes. I mentioned already twice, but I completely understand if you didn't hear me. This could be any judgment thesis. I just included an example, and I was lazy and I didn't write a big J, and that's confusing. Yes. We have to